This is the Proton Guru video practice for topic 2.6-9. These problems will give you practice on elimination reactions of alkyl halides. Some brief and straightforward reading to get you ready for these problems can be found in the Organic Chemistry 1 Primer 2018 in lessons 2.6-9. You can also find additional chemistry videos and information how to match up all these videos with your particular course's textbook to help you in your course at protonguru.com.
And now we move on to some questions about the E1 reaction. An E1 reaction occurs when 2-bromo-2-methylpropane is heated in water. And we're asked to provide an air-pushing mechanism leading to the major organic product. We know that the E1 reaction is a series of two steps. The first step is heterolysis, which would be the loss of bromide in this case. And the second step is electrophilic elimination. And this provides our alkene as the final product. We now have another E1 reaction question, and this time the substrate being heated in water is 3-bromo-2,2-dimethylbutane. Set this up. And we know that the first step of an E1 reaction is heterolysis, leading to the carbocation. In this case, our carbocation is secondary initially, and there is a tertiary carbon directly adjacent to it. This is the ideal condition for a carbocation rearrangement prior to any other steps of the reaction. We need to draw the resultant tertiary carbocation from the rearrangement. Only once that carbocation has rearranged to the more stable tertiary form are we ready to do the second step of the E1 sequence, that is the electrophilic elimination, and that gives us our final alkene product. Notice that I chose to take one of the hydrogens off of the more substituted carbon adjacent to the positively charged one to form my alkene between those two carbons. If you were to take off a proton from one of the methyl groups, the less substituted sites adjacent to the positively charged site, you would have a less substituted alkene like this, the non-Zaitsev product, and that would be a minor product. It is possible to form by an E1 mechanism from the substrate. We are asked to find the major product, so this would be the correct product in this case. Now we're moving on to some questions about the E2 reaction. And we're asked to provide the air-pushing mechanism and product for E2 reaction involving 2-bromo-3-methylbutane when it's heated with sodium ethoxide. We first need to recognize that sodium ethoxide is ionic and will break up into different ions because you have a metal-non-metal bond. The metal sodium will break off as the cation. The O2C2H5 part, the ethoxide part as it's called, will break off as the anion. We know that the E2 reaction needs a strong base, and this is in fact a strong base, stronger than hydroxide, which we know is probably the first strong base we've learned about. And we utilize that base to carry out the E2 mechanism, taking a proton off of the most substituted carbon that is adjacent to the leaving group site. And this leads to our final product very easily of this alkene. Now the fate of the base with the ethyl group on it is that it became ethanol, and our spectator ion, sodium, is still floating around. Our leaving group bromide has been pushed off as an anion, and now we have a balanced equation. One aspect of the E2 reaction mechanism is that the leaving group and the proton that are removed in the course of the reaction must be antiperiplanar to each other. This question is asking us to look at substrates and to determine which of these substrates might lack the required antiperiplanar leaving group proton pair, and therefore would not be able to do an E2 reaction. If we look at our first one, we see our leaving group is attached to this carbon, and we look at the adjacent carbons. The proton that's not drawn here, the hydrogen, is pointed the same way as the bromine, so it is not one that can be removed in an E2 process. If we look at the carbon on the other side of the leaving group carbon, there are two protons here, one of which is suitable to be removed by an E2 reaction because it is pointed the opposite direction, anti to that bromine. We look at the leaving group carbon in the second case, and we look at an adjacent site up here. These are both methyl groups, so those cannot be removed in E2 reaction. You need a proton on the adjacent carbon. If we look at the only other adjacent carbon next to the leaving group carbon here, we see that the proton is going away, which is the same direction as the bromine. They're both going away from the viewer. So we have no proton leaving group pair appropriate for an E2 reaction. So that substrate will not work for an E2 reaction. And a case like this on the far right, where you've got a leaving group and then neither of the two carbons adjacent to it even has a proton on it, that of course has no leaving group proton pair for E2 either. Now, in some cases, there are two possible E2 products for a given substrate. And a question like this is asking us, well, for each of these pairs, which would produce a greater excess of the non-Zaitsev or Hofmann product compared to the major product, the Zaitsev product? So if we look at the first pair, the only thing that's different, you have ionic compounds, a minus charge in the oxygen, substrates are the same, primary, secondary, and tertiary substrates all work for the E2 reaction. So the only difference is the base that we're using. They're both strong bases, but in the case of the bottom reaction, you have a very bulky base. With a very bulky base, you have a larger percentage of the minor product, the non-Zaitsev product, produced as a product of the reaction. If we look down at the bottom, we see the most obvious difference is we've got a really big bulky leaving group here. Compare that to the bromine. When you have a very, very bulky leaving group, it becomes difficult to position that leaving group and the hydrogen on the adjacent anti to it without some interaction between the bulky group and another part of the carbon chain. This is really what's called the Hofmann elimination reaction. And in such cases, you actually get the Hofmann product as the major product. So certainly we would say we have more of the non-Zaitsev product in this case.